Raw, unconstrained electrical energy is inherently violent. Before it is properly harnessed and standardized, it is entirely unpredictable. This chart visualizes a lithium-ion battery's raw performance output. It is highly unstable, heavily skewed by its immediate thermal state and its recent charge and discharge history. To extract usable engineering data, test facilities force these variables into alignment using a protocol called ISO 12405-4. If an OEM is evaluating battery systems from two competing suppliers, looking at uncalibrated performance data provides zero actionable insight. The comparison fails without a rigidly normalized baseline. ISO 12405-4 provides that baseline. It is an international test specification designed specifically to equalize the playing field for electric vehicle traction batteries. We are going to map the exact initialization protocol required by this standard, from the initial mathematical categorization of the pack through thermal equilibrium to the final standard cycle. Establishing this absolute ground truth is the mandatory prerequisite. Until this sequence is complete, a supplier cannot record or claim a single valid performance metric. Before a test engineer connects a single cable, they must mathematically define the device under test. This formula illustrates the standard's core ratio, maximum electric power output divided by electric energy output at a 1C discharge rate. A numerical ratio below 10 designates a high-energy system, typically mapping to battery electric vehicles and plug-in hybrids needing sustained energy delivery. Conversely, a ratio of 10 or greater designates a high-power system. This classification maps to hybrid electric vehicles and fuel cell vehicles, which demand rapid, intense bursts of power. This is a rigid categorization phase. A battery system cannot exist outside these two classifications. This single mathematical calculation dictates the severity and length of all subsequent electrical preconditioning steps on the test bench. Moving to the physical test bench, the battery pack is integrated using Class A and, if present, Class B high-voltage connections. There is a strict operational hierarchy here. The test bench equipment does not override the battery. Instead, it must follow the operational limits communicated directly by the battery control unit via the communication bus. Before any current flows through those lines, the pack must achieve thermal equilibration at room temperature. The battery pack must sit passively for exactly 1 hour. During this time, we watch for thermal convergence. All cell temperature measuring points inside the pack must settle to within a 2 Kelvin deviation from the ambient room temperature. During this stabilization hour, no active cooling loops can be engaged by the test equipment to force the temperature down. The equilibration must be natural. Until this internal thermodynamic baseline is verified across every single cell, any subsequent electrical testing will yield contaminated and invalid data. Once thermal readiness is confirmed, the system moves into an active phase known as preconditioning. The core purpose of preconditioning is to aggressively cycle the battery. This process mathematically erases its prior charge history and stabilizes the internal electrochemistry. This chart tracks preconditioning protocols based on mathematical categorization. On the left, high-power hybrid architectures require 5 deep cycles at a rapid 2C discharge rate. On the right, high-energy architectures require 3 wider, sustained cycles at a slower C3 rate. While the standard recommends these specific cycles, it does permit suppliers to suggest alternative currents if those match their internal factory testing. However, the cycling does not end simply because the required number of passes is reached. There is a strict performance gate. This chart isolates the mathematical exit criteria. The battery is legally considered preconditioned only when 2 consecutive discharges show a capacity difference of 3% or less. If the variance remains above 3%, the pack's chemistry is still drifting, the automated test halts, and the customer and supplier must intervene to agree on a procedure. Achieving this sub-3% variance proves the battery's internal electrochemistry is locked into a predictable, repeatable state. There is one final preparatory step required before executing any individual performance test: the standard cycle. The standard cycle normalizes the state of charge. This ensures that every single test begins from the exact same starting line. This diagram outlines the rigid standard cycle sequence: a standard discharge, followed by a 30-minute rest, a standard charge, and a final 30-minute rest. Those 30-minute rest periods are non-negotiable. They allow the internal cell temperatures and voltage levels to settle completely after a charge or discharge event. Once the standard cycle completes, it triggers a critical expiration window known as the 3-hour rule. The actual performance testing must commence within exactly 3 hours of the standard cycle's completion. If that 3-hour window is breached for any reason, the baseline is considered degraded. The entire standard cycle must be repeated from scratch. This tight temporal boundary guarantees the pack hasn't passively lost charge. It ensures engineers are testing the battery's active capabilities rather than its standby losses. Consider the sheer volume of labor required just to reach the starting line of a test. This flowchart tracks the complete initialization, defining the ratio, enforcing the thermal limit, locking capacity variance, and executing the standard cycle. Only at the end of this gauntlet does the standard permit engineers to measure energy, power, and efficiency. When an OEM reads a spec sheet boasting a specific rated capacity or an energy round-trip efficiency, those numbers are entirely meaningless without this rigorous precursor. Comparing battery systems without explicitly verifying their initialization protocols is an engineering failure. ISO 12405-4 dictates how to construct the mathematical foundation of truth required to evaluate the next generation of electric vehicles. The strict initialization baseline is permanently set and verified across the system. The true performance testing can finally begin.